Hello, everybody, and welcome back to another Mr. Farney Earth Science video. In the last video, we focused in on talking about how we can begin to group stars in different ways, such as star clusters, binary systems, constellations, and then we ran through the myriad of different characteristics of stars. In this video, we're going to move through stellar evolution, how stars form, how they maintain stability, and kind of walk through the life cycle of a star. So the whole thing with the star, if we're talking about its temperature, how bright it is, or its luminosity, its size, it's all governed by the mass. The more massive a star is, the larger the gravity is going to be, the higher the temperature, the higher the energy output, the amount of fuel it's going to burn is going to be much greater. So a star's mass governs pretty much all these other characteristics of a star, which is important because we need to keep several of these in balance or equilibrium, especially when we're talking about gravity or the pressure being put onto a star. It's really important that a star maintains an equilibrium. Otherwise, it'll either expand continuously and blow off its outer shell, or it's going to just kind of collapse and contract within itself. When a star is at this equilibrium, where you have an equal balance between internal and external forces, that's what we would call a star that is stable. So a star at equilibrium is going to be stable. If it's not at equilibrium, then it is an unstable star. Star formation, how does it form? It forms in one of these large clouds that are pictured down here in the bottom left that are really, really pretty. This cloud of interstellar gas and dust that we call a nebula. Nebulas can collapse within on themselves due to their own gravity. So nebulas have a lot of gravity within it, and it starts kind of condensing within itself. And as that cloud condenses and contracts, it begins to rotate, and that rotation forces it into a disk that's really hot. And as it kind of continues condensing, rotating, we can get what's called a protostar. And then once we have that protostar, we can begin burning different types of fuel once it gets hot enough. We have this process called nuclear fusion beginning to happen. Fusion is the process that stars use to burn fuel. Here on Earth, in nuclear power plants, we haven't yet found a very good way of doing nuclear fusion. We use nuclear fission, which we'll talk about in a later video when we get into renewable energy and things like that. But nuclear fusion is the process that stars use, to keep themselves alive. They burn first hydrogen. They will always fuse hydrogen into helium first. And then once this reaction begins, this fusion reaction starts, then a star becomes stable and we can place it on our main sequence. Every star begins as a nebula, which then forms a protostar. After a protostar stage, star will burn the hydrogen to helium until almost all the hydrogen is gone. This is the main sequence stage. This is the process of our main sequence stars, burning hydrogen until almost all of the hydrogen is gone. A star the size of our sun, it's going to remain in the main sequence for about 10 billion, billion years. That's a really long time. And judging from what we know about our star, we're probably about halfway through our star's life cycle in the main sequence. So in about 5 billion years or so, that's when it'll swell to a red giant, and then we'll move it out of the main sequence and move it more to the upper right-hand corner of the HR diagram. So right now, it's right here in the middle of the main sequence because our star is about, a 1 luminosity and its temperature is about 5,500 degrees Kelvin. And then once we're pretty much out of that hydrogen, going from hydrogen to helium, we're going to move it up here to the normal red giant stage. It is not massive enough in our main sequence to be put into the supergiant category. So again, we go from being in the main sequence to just kind of a normal red giant after we move out of the main sequence with our star. So again, what's the life cycle of a less massive star like our sun? Once that star is almost out of hydrogen, it starts to fuse helium, and that's when we begin having this expansion happen here. It forces the outer shell outward, and then it begins having some of the layers to expand and cool as it does that. It makes the star more luminous because it's getting bigger, but the temperature is decreasing. So even though our temperature is going down, which we say has a direct relationship with the brightness, because the star is getting bigger, it's getting brighter. So even though the star is technically cooler than it was previously, because it's bigger, it's going to be brighter. Once all the helium is gone, so we've gone from hydrogen to burning the helium, the lower mass star, it'll blow out its outer layer, forming a planetary nebula, which is pretty cool. And at the center of that planetary nebula, we'll have a white dwarf. Most of these white dwarfs are really, really small, but they're very, very hot. They're the size of the Earth. And then a white dwarf will last as long as it takes until it finally cools down enough and it becomes an undetectable black dwarf star. Really, really neat how it goes. This is a picture of a cat's eye nebula, okay, a planetary nebula. And at the center is one of those white dwarfs that we just mentioned in the previous slide. For more massive stars, they're going to burn their fuel very, very fast, much, much faster. Once we run out of hydrogen, our main fuel source, it's going to expand into a red giant that is really, really huge, a supergiant, we call it. The closest one to us is the star Beetlejuice, which you might have heard of before. It's part of the Orion constellation. So to put it in comparison, here's Beetlejuice, this really, really big star, and this very, very tiny pixel on our screen right there, that's our sun. And then these are some other stars that we've discovered kind of in our viewing sky, just to kind of put it in perspective of how small our sun is compared to a red supergiant like Beetlejuice. Once the supergiant runs out of gases to fuse, the core of the star is going to violently collapse in on itself. A neutron star will form in the core with the outer layers of gas surrounding it. And neutron stars are extremely dense, about 100 trillion times the density of water. Some of these neutron stars will have kind of pulsating light coming out of different ends of it. And as the star rotates, that light's going to be pulsing kind of in different directions. So as the star spins, we can see flashes of light of it from Earth. And we call these pulsating stars pulsars. They're really, really cool and not very found very frequently within the universe here. When all of the gases surrounding the neutron star are pressed inward because of the gravity, because it's very, very high gravity with this neutron star, it's going to kind of compress in and then explode outward in this huge, massive explosion called a supernova. We can see that these supernovas are even brighter than the galaxy it's in. It's very easy to see these supernovas, and this explosion creates extraordinarily dense elements. In this picture, the side by side is a very rare picture where we actually have a before supernova with this arrow was pointing to, and then during the supernova, which is in the left-hand side picture there. So it's very, very rare to have that. Some stars, they're too massive to form a neutron star to make that supernova happen. So when that star begins condensing in the middle, the really, really massive stars, they're not going to form a neutron star. It's this collapse is so violent and so quick that a black hole is going to form instead. So our massive stars, the most massive ones are the ones we're going to look for black hole formations. These are really small, extremely dense objects, so immense that nothing can escape it, not even light. That's why we can't see into or past what's called the event horizon of a black hole. That's the point where light gets trapped and we can't see into it, because light can't escape. And we use that light to be able to see what's going on. So we can't observe what's going on inside the black holes yet. We can only kind of observe what's being emitted from them. And we use X-ray telescopes to see kind of what's coming from black holes, which gives us pictures very similar to the ones that we see here in this image. And that's where we're going to end our slides for this. Okay. So life cycle of a star, what's going to happen with our star, our less massive ones, our massive stars, how we kind of get neutron stars, and then the most massive ones, how they can form black holes. So a lot of info in here. It warrants you going back, watching it a second time, I'm sure. If you have any questions for me, please go ahead and ask. If not, have a good rest of your day, and I'll check you out in the next video. Bye-bye.